Any general questions or problems? Anything? Okay, we were halfway through this problem basically. So just to refresh your memory, again, as is commonly the case with any acid-base problem, you know, the feature, right? Well, one of two features that makes it worth talking about as a separate topic is this obsession with pH, right? For any other kind of reaction, you wouldn't talk about pH, you'd ask about the concentration of the products typically, right? And so, you know, it's the special feature that makes this a little different, right? On the other hand, it's an equilibrium problem. All equilibrium problems have three parts. And so other than the fact that I have to know what this pH is, it doesn't change anything. I crossed out the number I found in the table just to emphasize the point that the basic question is really fairly simple, and therefore it is fairly deceptive if you don't fully speak the language, right? It does not give me it does not give me a balanced equation, right? It doesn't give me a lot of details about what's in the beaker. It simply asks me what the pH is of a solution. It doesn't mention the water, even though water is one of the reactants, right? It is implicitly in water because it's a solution. Right? And so if there's any, dare I say, trick to my acid-base problems, it is that a lot is left unsaid, right? But if it says pH, it is implicitly saying equilibrium, right? If it says pH, it is implicitly saying hydronium. And if it's molarity, it's implicitly saying there's water present, right? We will, at some point, maybe Friday, maybe Monday, talk about mixing acids and bases together, right? In this case, it's just a base, right? But because it's a base in water, and water is also both an acid and a base, right? That inherently gives me a reaction which gives me pH, right? Usually, this is not what I'm trying to do. I mean, there are times I might try to do this, right? If I wanted or needed something acidic because I was, you know, scrubbing my teeth or something, right? Then throwing an acid and water will give me a acidic solution. But typically I'm mixing an acid with a base because I'm trying to get the acid and the base to react with each other. And water is not usually my choice, right? But this reaction is always happening, at least in the background, even if my dominant reaction is between hydrochloric acid and ammonia, for example, right? But in this case, it's just ammonia and water. It's an equilibrium problem. All equilibrium problems have three parts, because you can never say that enough. We got as far as solving this and plugging the numbers back into my ice chart, right? And then we got to attempting to address the issue, right, of what the pH was. And this, again, is where it's helpful, I think, to write things down and label them, right? Because otherwise, my tendency might be to just take the log of one of the numbers I have, right? And frankly, you know, historically, the logical thing is to take the log of X. After all, I went through all that trouble to find X. But in fact, X does not represent hydronium, and pH has to be the concentration of hydronium. And in fact, if I look only at this reaction, I don't have any hydronium, right? I have ammonia, I have water, I have ammonium, and I have hydroxide, right? None of those things is actually hydronium. This reaction by itself actually does not create pH. Right? But this reaction is actually not by itself. Right? There's another acid-base pair in the water. That acid-base pair being the water. And so, as I very briefly introduced to you on Monday, right, in fact, water can react with itself. Right? Again, it doesn't know it's doing that. Molecules are dumb things, they just bump into things. But since water can donate a proton and water can accept a proton, if two waters bump into each other, it is possible for them to pass the proton. Right? So forget my ammonia and water. If I just have a glass of water, I have acid-base chemistry going on. It's this. Right? Because even though I only have water, I actually have an acid and a base. Just happens that they're both water. Right? This is essentially a Ka. It's also essentially a Kb. Right? Because it's water reacting with water as a base and it's water reacting with water as an acid. Right? As a result, to avoid confusion, it is usually labeled as a Kw, since it's all just water. Right? And like all equilibrium problems, right, there's an equilibrium expression, and hey, there's an ice chart if I choose to make it. And I think I will. Right? If I have pure, unadulterated water, there's nothing but water in my beaker. And so I have kind of a funky ice chart. Right? I can, as always, fill in the change line automatically. Right? And technically, you know, there's a minus X here and a minus X here. I don't really bother with them, mostly because, right, they're not in the equilibrium expression since it's a pure liquid, and so there's therefore no reason to track them. But again, since they are the solvent, the amount of water really isn't changing very much. There's a whole lot of it, right? And so I have kind of a funky ice chart where it looks like I'm starting with nothing, right? If I don't include the water, right? There's initially no hydronium before this reaction happens. There's initially no hydroxide before this reaction happens, right? I make both of them just from the water. And so I can solve this. I don't even have to make an assumption, right? My Kw is just x squared, so square root of 10 to the minus 14 is 10 to the minus 7, right? And so if you have pure unadulterated water, right, in fact, there's a little bit of hydroxide and a little bit of hydronium in the water, right? And in fact, since there's hydronium, it is reasonable to calculate the pH for the water solution. If you do this, you get 7. Now, I don't always know all the lies you might have been told in high school, right? There tends to be, and I think it's more an earth science thing than a high school chemistry thing, this conception, this pH scale is just a way of ranking acids, and it's 7 in the middle, and it goes from 0 to 14. Not really true, right? In fact, the pH scale really goes from about -2 to about 23, right? But more to the point, 7 isn't in the middle of the pH scale because I put 7 in the middle of the pH scale. 7 is quote unquote neutral because it is the natural amount of hydronium that's in a beaker of water because of this equilibrium. Right. Now, right, that being said, my original problem, the ammonia in water, was not this situation, right? This is pure unadulterated water, right? And so, in fact, if I have ammonia in water, I really have both equilibria, right? In essence, because I don't usually start doing this now, but maybe I should, right? In essence, it's because, again, molecules don't make decisions, right? You will, in the end, be dominated, right, by the reaction that's dominant, right? If you've got something with a giant K, it's going to naturally dominate, right? But it doesn't do it by choice. It just ends up dominating because that's the way the equation's balanced, right? In essence, if you've got multiple acids and multiple bases, we will at some point get to the question, what's the best acid, what's the best base? I expect those to dominate, but not because the acid and the base knows they're supposed to dominate, right? In fact, if an acid bumps into a base, there might be a proton transfer. So frankly, every acid in a beaker reacts with every base in a beaker. In this particular case, right, it's really three compounds, if I want to classify them this way, that are in the beaker. There's ammonia, which is the only thing I added to my water, which is itself a base, right? And there's water, which I want to count twice, right? Because water is both an acid and a base. And so I essentially have two bases with one acid, and there is no reason for the molecules to choose to only do one thing, right? And so, in fact, they don't. They do both things, right? It just happens that one of them dominates, right? In fact, if I go all the way back, I don't want to go all the way back because you don't want me to go all the way back. But if I go back to my acetic acid, which was my acid example, right? Technically, that was a case where there was two acids and one base, right? The only base was the water, but I also had acetic acid as an acid and water as an acid. In fact, both of those reactions were also happening. I didn't bother to mention the second one, not because it wasn't happening, but because it's so small, it doesn't create much hydronium beyond what I had from the first reaction. All right. The only reason I need to consider it here is because my first reaction doesn't give me any hydronium, right? If my question were different, right, which is how much hydroxide do I get from my ammonia solution, I wouldn't consider KW either because it's not going to give me any hydroxide to speak of. But it does give me the only hydronium that I have. Right? And so there's really always these two reactions going on because the water reaction is in background. There are just a lot of times where I don't bother with the water reaction because it doesn't change much of anything. If I have a base like I do here, it does change the hydronium concentration. It's the only hydronium I have. Right? And so I kind of want to do this more than is on the slides. So I will. What's on the slide is mostly my shortcut, and we talk about the long cut later. But again, there's no reason not to go the long way now. There's a question in the chat, is the pH of pure water always literally exactly 7.000? Depends on how you mean that. Yeah. by which I mean if you're asking me if theoretically the pH of water is always 7.000, the answer is yes. If you're telling me, if you're asking me, will you always measure a pH for pure water of 7.000, the answer is no. Right? Because in fact, you almost never have pure water. Even distilled water fresh from the tap is not pure water. Anybody know why I say that?
Gases?
Well, if it's distilled water, there's presumably not other compounds in there, but in my ear, there are dissolved gases. Right? If I'm in a room with gases, there's always dissolved gases. And so it's never water with nothing else in it. At the very least, even if I don't have any of the byproducts of the purification, right, there's dissolved gases, of which the big one is carbon dioxide. Because as many of you know, or should know, since it was your project, sort of, right, if carbon dioxide dissolves in water, it forms carbonic acid. And so if you take quote unquote pure water, you will always measure an acidic pH unless you do something to get rid of the dissolved gases. Well, I never said faucet water. Faucet water has a lot of ions in it, if nothing else, fluoride. And if you have well water, God forbid. Anyway, getting back to my original problem, which was my KW, this reaction is technically happening, right? And again, I wouldn't bother much with it, right? Except for the fact that, right, it's my only source of hydronium. Right. It is not, however, my only source of hydroxide. In fact, I have hydroxide. Now I got to remember 00211, I think. I have hydroxide from the ammonia reaction. Right. And so, you know, it's an equilibrium problem. All equilibrium problems have three parts. And so if I really wanted to do this the long, hard, honest, true way, right, I could. Right. And if I do, here's a good place to make the assumption, right? If I assume x is small relative to 0.00211, this is just x times 0.00211, is 10 to the minus 14. Right? If I do the math there, and I'll give you a second to catch up if you're writing it down. If I do the math there, x is just 10 to the minus 14 divided by 2 times 10 to the minus 11. Or, if you prefer, and maybe you do, right, just didn't quite fit. Minus, it's 10 to the minus 11, 13, 10 to the minus 12. Now, of course, there's always the question of, is it a good assumption? And of course, if I divide that by 20, I get 0.0001. Hell yeah. It's 100 million times smaller than small. Right? And this is why I say, in the normal scheme of things, right, my KW reaction isn't doing a lot acid base wise if I have anything else present, right? But if my other species, in this case, the ammonia, is a base, right, it doesn't change the hydroxide any, which is why when I add an acid, I didn't bother with it because it didn't change the hydronium any, right? What it does, however, change is the hydronium because my reference is 0 for the hydronium. So, hey, you know what? The hydroxide is unchanged unless I happen to have 10 significant figures. On the other hand, that's 100% of my hydronium. And so even though it's not a lot, it's all I've got. Like the $17 in my pocket. It's not a lot, but it's all I've got. I've been oddly obsessed with the $17 in my pocket since Monday when I took it out in my 1 o'clock class and I said, well, I've got $20. And I looked, I said, no, I only have 17. And I feel bad because I felt poor at 17. Anyway, and if I had 5 times 10 to the minus $12 in my pocket, I'd feel even poorer. On the other hand, it would be the only money I had. Right? And so in general, I don't worry about this reaction, right? Unless one of two things is true, right? Which is I don't have very much hydronium from my first reaction, which you'll see later today or Friday, or it's a base. Because if I added a base to water, this is the only place I get hydronium. Yes, no, maybe. I don't know why. Now, right, since it didn't really change the hydroxide any, right, essentially there's a shortcut to solving that ice chart I actually solved. This is the shortcut, right? Technically, this is really just the log of the KW equation, right? Because again, if I'm going to satisfy the equilibrium for the water reaction, this has to be true. And so the product of the hydronium and the hydroxide is always 10 to the minus 14. If I have another acid in there, the amount of hydronium goes up because of the other reaction, and that forces the hydroxide to go down. On the other hand, if I have another base present like the ammonia, the hydroxide goes up, which forces the hydronium to go down, right? That's what I just saw when I did the ice chart, right? Which is my hydroxide was all the way up to 0.00211. Oops. which made my hydronium go all the way down to 10 to the minus 12. Notice, right, again, if it was pure unadulterated water, these would be equal. Right? And so this is where, you know, you get that sort of semi-true high school chemistry thing that says bases, you know, have hydroxide, right? Acids have H plus. Really, they all have both. It's just a question of which one has the bigger amount. Right? And so the shorthand of this is really to essentially pre-solve my KW. If I take the negative log of my KW expression, right? The log of a product is the sum of the logs. The log of 10 to the minus 14 is 14, right? Well, this is pH, right? By definition, the negative log of hydronium is the pH, right? And this negative log of hydroxide is generally termed the POH, as you will find out for some math reason, some historical math reason. P of anything is the negative log of whatever the anything is, right? P of my $17 of my dollars is negative log of my dollars, right? So my P dollars is negative log of 17, right? That gives me a shorthand to avoid solving the second equilibrium problem, right? I had, from the first equilibrium problem, the concentration of hydroxide. Again, the sum of the POH and the sum of the pH should be 14. And so rather than go through and solve the entire ice chart, not that that took me a whole lot of time, right? I can very quickly calculate the POH, right? It's just the negative log of the hydroxide, and I subtract that from 14, right? Which gives me a pH of 11.33, right? Very little hydronium, but some, right? Approximately 5 times 10 to the minus 12. Right, it's worth mentioning, all right, all K values depend on temperature. So technically speaking, that little algebraic expression is not, again, some global truth. It's true at 298 Kelvin, standard temperature. And if you want another little, oh my gosh, you know, I learned something new on Wednesday, right? The neutral pH for boiling water is not 7. My headset is making funny sounds. Can you still hear me at home?
Yep, we can still hear you.
Okay, good. It keeps beeping in my ear for some reason. Right, because, right, that 7 comes from this, and this is only technically good at 298 Kelvin. And so quite naturally, neutral pH, which really is not so much a magic number as it is the point where the hydronium equals the hydroxide, right? Which is always the square root of KW, right? At different temperatures, neutral pH is different. You don't even have to go to boiling, right? Right now in this room, which is not 25 degrees, it's more like 20 degrees Celsius, right? KW is probably slightly different than 10 to the minus 14, which means even if I have gasless, pure water in this room, I'm not going to get 7.000. I wouldn't expect to. All right. There's another useful property of Kw beyond determining the pH of a base, and that gets back to what we were talking about just in general for these reactions. Technically speaking, right, my Ka and Kb reactions are really pairs of acids and bases, right? Because the reactants are an acid and a base, and technically the products are also an acid and a base, right? And so I really have two acids and two bases, right? And so, again, they technically termed conjugate, right? This is the conjugate base for this acid. But as I'm fond of saying, I hate that C word, because a base is a base and an acid is an acid. I don't really need to demean it by calling it the conjugate, right? If I started with just the A minus, right? I don't do this reaction at all, in other words. If I just
acid, right? The conjugate, you know, is acetate. If I just throw acetate in water and there's no acetic acid, there soon will be, because the acetate is itself a base. And I don't need it to be conjugated to be a base. It's just a base. And so it's in water. It will react with the water. When it reacts with the water, it makes acetic acid. And so one of the things I say a lot starting next week is it is really helpful if I learn to think of my acids and bases not as acids and bases, but as pairs of compounds, right? In other words, right, I don't want to think of acetic acid as acetic acid. I want to think of acetic acid as acetic acid and acetate, right? It's a conjugate acid-base pair, right? And it's helpful to think of them as a pair because it doesn't really matter which one I start with, I get the other one, right? If I put acetic acid in water, right? Hey, it's an acid, water's a base, there's a proton transfer from the acid to the base. Hey, look, I got acetate. If I put acetate in water, hey, it's a base, water's now an acid, proton goes from the water to the acetate. Hey, look, I made acetic acid. And so in a very real sense, I never have one of the pair in water. If I start with acetic acid in water, I get both acetate and acetic acid. If I start with acetate in water, I get both acetate and acetic acid. All right, and so they're really, hence the term conjugate, a married pair of compounds. If I'm in water, I always have both. And it doesn't matter which one I start with, I will end up with both. All right. I won't have equal amounts of both because it's going to depend on the equilibrium constant, but I will have at least some of both. All right. And the reason that becomes an issue is one of those quirky things that the internet might have fixed. Right? Which is, even though technically this is a base, right? I will find the acid, which is the dominant partner here, because it has the bigger K, on my list of acids, right? I generally will not find the acetate in my table of bases. again, the internet being, a large place with room for all kinds of weird factoids, probably will have it listed somewhere, right? But generally speaking, right, if I go to a list of acids, it tends to list the classical acid and the conjugate of that acid, because every acid has a conjugate, is generally not included in the list of bases. And so that's not a huge issue, right? Because technically Kw is the relationship between the two, right? Because I always have both if I react it with water. And so, again, I show you the derivation, I don't hold you responsible for it, right? Here is the Ka of some acid. Here's the Kb for the conjugate, right? Again, if it's a Ka, it has to be reacting with water. If it's a Kb, it has to be reacting with water. And so my other reactant in both cases is the water, right? If you prefer a specific example, again, here's my acetic acid and acetate, right? My acetic acid in water gives me acetate. My acetate with water gives me acetic acid. If I actually combine those two reactions, right? Look, there's acetic acid on the left, there's acetic acid on the right, that cancels. There's acetate on the left, there's acetate on the right, that cancels. If I add those two reactions, I get Kw. Which is why historically, nobody bothers to list acetate separately, right? Because the Kb of acetate can be easily calculated from the Ka of acetic acid, right? If I add the two reactions, right, I essentially multiply the Ks, right? Because I have now all of the reactants from both reactions, and I have all of the products from both reactions, right? But again, everything except the water reaction cancels, right? And so, again, only for a conjugate pair, the Ka of the acid times the Kb of its conjugate, right? So this has to be acetic acid and acetate, right? It's not any old acid with any old base. But if I take the Ka of the conjugate and the Kb of its conjugate multiplied together, I always get Kw. And so this becomes useful if I happen to be starting with acetate instead of acetic acid. In the end, I end up with both, right? But again, historically, I don't always get handed the value in a table because it is quite common to ignore the conjugates when I construct my tables of acids and bases, right? And right. And we will use that eventually, but no reason not to at least mention it now. And you now know essentially everything there is to know about acids and bases, except for one thing, which we won't get to today, but soon. Right. Right. And so, right, I can do somewhat more advanced things with it, but they're really not much more advanced. Because in the end, they're all just equilibria, and all equilibria problems have three parts, right? Even if I have multiple things going on, which I just did, right? I had ammonia reacting with water and I had water reacting with water. I solved them separately. right? And we'll talk much more about that going forward, right? Because in general, I can do that. As long as the K values are different enough. Right? And so I never really do anything other than what I've been doing. If it's an equilibrium problem, it has three parts. I write a balanced equation, I write a K equation, I write an ice chart, I solve. If I have 10 different acids and 10 different bases, that's 100 possible reactions. You know what that is? That's 100 three-part problems, maybe. Right? Because every acid could react with every base, but I solved them all separately. As long as the K values are different enough. And so there are these things called polyprotic acids, as well as polyprotic bases. Right? Meaning they have more than one proton they could donate, or more than one proton they could accept, depending on whether it's an acid or a base. This really doesn't change anything. It just gives me extra steps because I'm going to solve them as separate reactions, right? So these are probably the most common of the polyprotic acids. I mentioned sulfuric acid the other day, right? You will notice, by the way, they are all, with the exception of hydrogen sulfide, right? They're all hydrogen polyprotic, excuse me, they're all hydrogen polyatomic ion, right? But in this case, the polyatomic ion happens to have a charge greater than 1, right? So, you know, when I had HClO4, just so happened ClO4 minus, my polyatomic ion was a -1. Sulfate's a -2. If I'm going to make a neutral compound out of sulfate, I need 2 positive charges, not 1, right? Phosphate, PO4, has a -3 charge. If I'm going to make a neutral compound out of it, I need 3 positive charges, therefore 3 protons, right? This really doesn't change anything because I'm not going to take them all off at once. Right? So if I look at something like phosphoric acid, where you might be in your room going, holy crap, 3 protons. Well, yes, and therefore 3 Ka reactions. But that's good news, not bad, because if I had one reaction where all 3 came off, my stoichiometry is more complicated, right? In fact, it's simpler if I have 3 successive monoproton donations. And frankly, it only makes sense, right? I can't donate my second proton till I donate my first proton, by definition, because the first one that comes off is going to be the first proton, right? And so if I have phosphoric acid and water, phosphoric acid, in its very name, is an acid. Water becomes the default base. I transfer a proton from the acid to the base, and what do I get? Good old hydronium and dihydrogen phosphate, H2PO4 minus, which is still essentially a hydrogen polyatomic. It's still an acid. And so if my dihydrogen phosphate bumps into a water molecule, it can transfer yet another proton, which gives me hydrogen phosphate and more hydronium. All right. But hey, guess what? Hydrogen phosphate is still hydrogen polyatomic. And so if it bumped into yet a third water molecule, there's a third proton that can come off. Right. If I go to my table of acids and bases, it will give me the same number of Kas as I have acidic protons. Right. Each one referring to, right, one of the protons coming off. So if you look up phosphoric acid in your book or on the internet, you'll find a Ka1, a Ka2, and a Ka3. The Ka1 corresponds to the first proton leaving. The Ka2 corresponds to the second proton leaving, and my good old Ka3 corresponds to the third proton leaving. Right. You will notice, right, there is a significant difference in the K values. Right. I mean, it makes sense if you think about it. After all, my second proton donation is an H plus, emphasis on plus. It's an H plus leaving an anion, right? Because my dihydrogen phosphate has a negative charge, right? And so it should be, if you will, harder to take off the second proton, because I'm now making it even more negative by removing a positive charge. The positive charge should want to stay, right? And then my next one is a -2 charge. It should be even harder to take off the third proton. And the K values prove that it is. In the case of phosphoric acid, they are significantly different, about a factor of 100,000 between each one. And because of that big difference, right, it makes it far more logical to treat them as separate reactions, because the second reaction is not going to upset the first equilibrium. What do I mean by that? Hopefully we have just enough time to find out, right? So again, my question, as always, is what's the pH? Right. If it happens to be something like phosphoric acid, which is polyprotic, right? First of all, I'm going to find out phosphoric acid is polyprotic, even if I don't know, when I go look it up in the table for Ks. Because when I go look up the K values, it's going to give me 3 of them. Right? That's really explicitly telling me that 3 protons come off, right? And so I'm not going to panic. I'm not going to get nervous. I'm not going to do anything crazy, right? Because all equilibrium problems have 3 parts. And as long as I do them one at a time, as I'm fond of saying, it's not harder, it's just longer. I have 3 3-part problems. But so what? If I know how to solve one of them, I know how to solve 3 of them, it's just going to take me a little more time. Right? The only addendum to that is they're not 3 separate reactions, they're 3 consecutive reactions. Right? Because my first reaction actually makes the reactant for the second reaction. And both reactions make hydronium. And so the second reaction really starts where the first one ends. And the third reaction starts where the second one ends. And so they're consecutive, and my ice charts feed into each other. But other than that, it's just a 3-step problem that I already know how to solve, right? There's my initial concentration of the phosphoric acid. Implicitly, there's none of the products yet. I just started. It's in water. -x, -x, plus x, and plus x. I plus c equals E. All I got to do is solve for x, and as is frequently the case in problems of the second type. All right. My K equation, if I know the equilibrium constant, all right, allows me to write one equation with one unknown, which I can solve. All right. In this particular case, my assumption fails. Breaks my heart, but it does. All right, if I assume x is much less than 0.1, I get 0.0274, right? Again, 5% of 0.1. All right, it's 0.005. All right, 0.027 is greater than 0.005, so it fails. So apologies to people who like to copy down all the algebra. right? I have to do it, Wolfram alpha, graphing calculator, or quadratic equation. Again, I get 2 roots, as I should from any quadratic, right? This root makes no sense in the ice chart because it would give me a negative amount of hydronium, right? And so the only solution that makes sense is the 2.39 times 10 to the minus 2. And so if I put it back in my ice chart, I'm all but done with my first reaction, right? And I would be all done with the problem, except for the fact that dihydrogen phosphate is itself an acid. And so I still have water. I now have a brand new acid, which I just made in the first reaction. And so there's no reason it won't also react with water, all right? But again, it's just a nearly completely separate 3-part problem, all right? The only thing that makes it less than completely separate is the fact that this is the reactant in the second reaction, and this is a product. And since I'm treating it as though this reaction has happened and is over, right, what I end up with here is what I start with here. Right. My initial concentration of dihydrogen phosphate is the equilibrium concentration from the first reaction, and my initial amount of hydronium, right, is again the equilibrium amount of hydronium from the first reaction. Not to keep you longer and belabor the point, we will wrap that up on Friday, right? But then once I do the second one, I can go on to the third one, do the same thing. One reaction follows the other. I treat them, however, as separate, other than the fact that my end point for the first reaction is the beginning point for the second reaction, and the end point for the second reaction is the beginning point of the third reaction. Questions or problems? Somehow I'm always 2 minutes over.
Have a great day.
Happy Wednesday.